Hey guys, and welcome to day 6 of our online learning. A couple things that we're doing a little differently. So number one, we're starting our new unit. It's called, it's gravity. It's universal gravitation. This unit's going to last a week and a half, so it's very quick, but we do have a couple big concepts to cover. We will finish with this after next week, and that will give us a few weeks left in order to talk about electricity. And yeah, that's it. This is now under online learning for gravity, and there's a couple things to check out. So number one, the slides that I will be using are right here. Please refer to them if you have any questions or get a little lost. The second thing, today's assignment, we are going to read a short one-page article, and we are going to answer some questions about that article. This is for a grade. Double check the rubric if you are kind of keeping track of your grades, especially on sort of these assignments that look that aren't very similar to the quizzes and tests that we've done in class. For those assignments, I would really recommend checking out your rubric to see what that's going to look like. Next thing, attendance assignment. I thought we would do something a little differently today. Probably some of you had this happen in other classes before. So instead of having our typical Google form, which while I love reading, doesn't really give you a chance to interact with anyone else in class. So today we're going to do kind of like an online question board. So I haven't posted a question to you. Instead, I would like you to ask one question you have about black holes. Now, this can be anything. The only thing, though, is that a question cannot be posted more than once. So if person A asks, how do black holes form? Nobody else can ask that. The next thing, you all have to answer one question, one person's question about black holes. So you have to both ask a question and you also have to answer a question. Do this in order to be counted present for today. I just know that for most of my classes, this is a topic that people are actually into as far as physics go. And I would hate for us to miss out on what would have probably been a whole class time of just random discussion, Q&A, all the fun things, all the sci-fi novels, without having just kind of a small replacement for that. So this is your attendance. Just ask one question, answer a question. It can be any question. Make sure you use appropriate language. Thank you. All right, let's go ahead and take a look at our slides. So I'm just going to go over a few things here, which I already had open. Okay, so we're starting universal gravitation. This takes forever to load. There we go. We've got two main goals. One of them is using the universal law of gravitation as described by Newton, and the second one is Kepler's laws, which you may or may not be familiar with from chemistry. But again, it's a week and a half unit, so we're gonna cover it quick. All right, here's just some fun quotes I like. Big fan of Jules Verne, so I put them in there. All right, so what is gravity? Gravity is one of the main forces of the universe. There are 4 main forces, as you remember, and gravity is actually the weakest of those. Gravity is basically what describes how masses interact with each other, specifically how one mass can be attracted to each other, and how that relates to the object's mass and the distance between them. This is our equation, because we always have one. Okay, let's go into this. So the force of gravity. Before now, we have talked about how gravity mostly in terms of the acceleration here on Earth. Now we're going to be looking at the gravitational pull of objects. So the force of this pull is equal to big G, and big G is a constant. So yay for constants, which just means numbers that we get to plug in and not memorize. Big G is a very, very small number. It's 6.7 times 10 to the negative 11th. I would recommend putting this just like this in your calculator and not relying on the idea of counting out just 11 zeros, okay, or 10 zeros. So we have big G, and that's multiplied by different things. So we have mass 1 and mass 2. So two different objects within space. It's usually what we're going to look at as planets and moons, maybe asteroids. And we're going to look at the mass of object 1 multiplied by the mass of object 2. Then we're going to divide that by the distance between the center of those objects, so between the core of those objects. And we're going to square that. So make sure we're multiplying these separately, squaring this separately, dividing those together, getting something, multiplying it by big G. Again, we will practice with the equation in the future, but not today. Okay, a couple fun things. Because big G is so small, even though gravity is literally the reason we have our entire universe, it's still the weakest force out there. So we talked about how you guys, and everything with mass really, has a gravitational pull. So I have a gravitational pull on the molecules in this room right now. However, I am not a very big mass. And the mass between the particles and the mass between me isn't very large. Or the distance, really. And also G is very small. So typically speaking, we're only going to talk about gravity in terms of objects with really, really large masses and really, really large distances, because those two things are able to sort of see that gravitational effect, because again, G is so small. So we're mostly looking at planet-sized masses. A couple of things. So the gravitational pull on objects gets really, really small as distance increases, the distance between them. This is called an inverse square force law, or just an inverse square law, which is 1 over r squared. Basically, if I increase the distance between two objects, like if we got 10 times further away from the sun than we currently are now, then our gravity would decrease by 100 times. So you start getting these really, really big effects. As one increases, the other one decreases. And they don't just increase or decrease proportionally, one of them exponentially does it. All right. Electricity has a field, magnetism has a field, and so does gravity. Forces exert fields, create fields. We're talking about gravity. So first off, when we're talking about Earth, it's going to vary a little bit with height. So areas that you see in red actually have a little bit higher of an acceleration due to gravity than areas that are in dark blue. Other things. So going forward, we're going to be talking a little bit about space-time. And if you haven't heard this metaphor before, then it can be a little tricky. So the idea is that space and time are interrelated, not necessarily time that we think of as being on a clock, but just space and time together. They can be affected by each other. Space-time looks kind of like a blanket. Think of like a picnic blanket. And objects that have mass, a whole lot of mass, are placed on that blanket, and they are able to push it down. So the Earth, because it has a great mass, we can see kind of here, pushes down on the space-time, and this is part of gravity. Okay, so quick thing about how they were able to figure out what big G was. I think this is really cool, especially the fact that it happened in 1800. You know, you just really don't get enough credit to these people who had to figure out things without any kind of technology. So this guy, Henry Cavendish, was a British physicist in the very late 1700s, who weighed the Earth, but not really. So this is his experimental setup. Basically, there are these little small masses. They're very, very small, the ones in green. And he let them be put on a string, which was able to rotate. So this string was able to twist around and rotate. And they sort of oscillated back and forth. Next, he had really two very heavy fixed masses. He was able to determine the angle of the mirror. He was able to, using the mirror, calculate the angle that the small objects turned in order to get closer to the heavier fixed masses, which they did. He's able to use this calculation and find the actual, or pretty close to the actual, it disappeared. Big G, the universal gravitational constant, 6.754 times 10 to the negative 11th. And again, we're not memorizing that number. All right, for the topic we're all excited about, what are black holes? So a black hole is any region in space where the pull of gravity is so strong that light is not able to escape. In fact, no electromagnetic waves are able to escape and no matter is. And this slide is not finished. That's fine. I'll just talk about it. So essentially what happens, black holes, to the best of our knowledge, and you have to understand, a lot of stuff about black holes is either theoretical, it's based upon what we know about the universe and what math says about the universe, how it should work. And we're still collecting evidence, but people are collecting more and more evidence every day for how black holes function, how they form, and what happens inside of them. So we're getting closer to understanding them, but this isn't like a done deal. Like a lot of things in physics, we haven't already figured this out. Okay, here is a great video. I would recommend watching it. I know you guys are bored. Watch the cool video on black holes, please. So, if you remember from our nuclear unit, there's nuclear fusion, right? Atoms fusing together to make larger substances. Our sun is entirely unremarkable. Sorry. And the only thing it's really good at doing is fusing hydrogen atoms together into helium. However, larger stars can create heavier elements. The type of stars that are able to sort of become black holes are ones in which can form the heavier elements, such as iron. These are elements in which it takes so much energy and so much pressure and heat in order to form that they have to be massive. And the reason for it is this. So nuclear fusion is a balance inside stars. They have to have both an outward pressure and the inward pull of gravity, right? Because it's a mass, so it has gravity pulling it together on the inside. This is how gravity helps shape our whole universe. It formed the stars and then the planets and then set them in motion around each other. However, eventually all stars must die and stars run out of fuel. Whenever this happens, the core of those stars, and again, I'm summarizing a lot here, okay? The core of stars is going to condense and it's going to become very hot and very dense at this point. Eventually, that reaction is going to explode outwards because you're forcing all of these atomic nuclei in such close precision to each other that they're almost overlapping on top of each other. And eventually that buildup of that many atoms closely packed together, especially that many heavy atoms, is going to cause a nuclear sort of fission explosion. And we have a supernova. Now, depending on how big the star is, a lot of things can happen after a supernova. But the one we're concerned with is what happens to massive stars. So if we're thinking about massive stars, like 10 times the size of our sun, they have no more outward pressure to sort of force them outwards. There's nothing left. However, they still have that really, really strong gravitational pull. And since gravity is related to mass and they're massive, then they have that gravitational pull is able to pull in so much until it forms a sinkhole of both energy and matter, which is a black hole. So black holes, super trippy, let's just say. I won't ruin all the fun things. That way you guys have questions to come up with and questions to research, but just a few of the cool things. So number one, we talk about black holes. They're areas of which the gravitational pull is super, super intense, and they're also the densest things in our universe. General relativity predicted actually that a dense enough area can deform space-time. So if we think about space-time being like a blanket, really heavy objects sort of sitting on top of that, weighing it down, the masses sort of wrapping space-time around them, then we can talk about how black holes are maybe able to rip through space-time. They experience what's called time dilation, which is I think we've talked about it a little bit in class maybe, how if I am here on Earth and I have a twin and my twin goes out into space as an astronaut, then as they approach the speed of light, then time for them slows down so that if they were to return back to Earth, they would perhaps be younger than their twin, younger than me. This is all, again, the kind of stuff that happens once we hit things like nuclear fusion reactors in our spaceships, which is a long way off, so we're working on it. Until then, it's just a really, really good sci-fi idea. All right, so all black holes have in the event horizon just the point where light cannot escape. You'd have to travel faster than the speed of light. However, that's impossible, and so therefore, none of it ever does. Since light is the fastest thing in the universe, if light's not getting out, then nothing else is either. That includes all types of mass, all other types of electromagnetic waves, anything traveling through space, until finally you get to a point of singularity, which is a point where gravity approaches infinity for what seems like an infinite amount of time. Now, the cool thing about black holes is that you can't actually see them, right? You have to have light in order to see something. So because of this, they cannot be seen. The only thing that can be seen is the event horizon. We were able to detect black holes through a number of ways, but one of the big ones is that as matter is drawn towards a black hole, it becomes heated to such a point that it emits X-rays. And those X-rays from around the event horizon can be detected through space. All right, a couple other weird things. Quick note as far as just busting some general sort of misconceptions. Black holes do not slowly suck everything around them. They have imagine it this way. So let's pretend that our sun was big enough to become a black hole. If it becomes that, then it has all of the sun's mass, all of the sun's energy, but instead of existing as how big the sun is, it shrank to a point smaller than like a period on a page, right? So all of that mass, all that energy now concentrated in a very, very small area. And this is where black holes get really weird because matter is supposed to be stuff and you can't just stack stuff up. So who knows? So all the sun's mass, all of the sun's gravitational pull is just now confined into a really, really dense, compact area. But we're not getting closer to the sun, are we? And therefore, that black hole, it would have no effect on us. So you don't have black holes just gobbling away planets. Only planets or objects that were already rotating close enough to them that they would have been pulled in past that event horizon would have been affected. So things still orbit black holes. And they do it in the same way that they used to orbit those stars once they existed, as long as they were out past the event horizon. Boom. So great. And with that, we're going to stop there. All right, so your assignment is to, again, read this article. It's a short one page, and let's face it, like half of it's pictures, guys. And then after that, answer these questions. You all have a copy. There's a couple of things you were supposed to measure using a ruler on your diagram. However, I went ahead and just measured them when I printed it out and gave you the figures right here. You don't actually have to calculate anything with them. You're just sort of describing how they relate to each other. So which one's bigger? What proportion are they bigger? Things like that. Let me know if you have any questions and feel free to stop in for office hours. I like hearing from you guys.